metabolism, the definition is just a series of reactions that are happening in your body. And in a cell, there are two types of reactions that can happen. The first is called catabolic reactions. In catabolic reactions, a compound is broken down into its smaller parts. So if you have something like A, B, it's broken down into A plus B. Now the second type of reaction is just the opposite. It's called an anabolic reaction. And in anabolic reactions, instead of breaking down, you're building up using smaller parts. So you have A plus B turning into AB. Now let's look at the energy concept behind this. Here, with this large compound AB, it's actually a lot less stable and has a lot more energy, and it wants to turn into these smaller parts. So because you're going from a large, high energy molecule to its smaller pieces, catabolic reactions are always exothermic. Now the exact opposite in anabolic. You have stable, low energy molecules turning into a large, unstable, high energy compound. And when I say unstable, I mean it's less stable than before, not necessarily unstable. So here, this is always endothermic. Now what really is energy? Now energy is really hard to define, but most definitions say energy is the capacity to do work. Now you might think that in our body, why can't this energy just be recycled throughout our body? But all the reactions that are happening in our body, they're not always all effective. So some of the energy that is used in reactions actually leaves your body as heat. And this is the same thing that happens in an ecosystem. We have energy entering in the form of light energy, and then some of the energy is leaving as heat. So energy cannot be recycled, and this is the opposite of matter, which is just recycled throughout our bodies and an ecosystem. So when we're talking about energy, there's two laws that we have to focus on. The first law of thermodynamics, which is just all energy is conserved. And this can be broken down into energy can never be created or destroyed. The energy in the universe is always constant. Now the second law states that the entropy in the universe is always increasing. So the concept of entropy can sometimes be hard to understand. So entropy is actually, if you took AP Chem, you know entropy is defined as, S stands for entropy, is K times ln W. And K is just a constant, and W is the number of microstates. And basically what this is saying is if you have a molecule, the entropy is just how many different locations or how many different ways it can be arranged. So if you have a solid, you can't really change that or disorganize that or anything. But if this solid turns into a gas, this gas molecule, on the other hand, has lots of microstates. It can always be moving around in whatever container it's in, and it has a lot more microstates. So when you go from a solid to gas, since the microstates increase, the entropy increases. On the other hand, if you have a gas molecule turning into a liquid or a solid, you're restricting the amount of microstates it has. Therefore, entropy would be decreasing. So now that we understand the concept of entropy, we can look at Gibbs free energy. And everyone knows this equation, delta G is equal to delta H minus T delta S. Now, an interesting thing about this term, T delta S, is delta S is actually equal to delta Q over T. So once we cancel out these values, this term actually is just delta Q, and Q is heat energy. So in this equation, you have delta H, which is the total amount of energy, and then we subtract from that heat energy. So what free energy actually is all the energy that you have minus the energy that you can't use, so you get the amount of free energy, the energy that can actually be used to perform work in a cell. So in this equation, we need delta G to be negative for the reaction to be thermodynamically favorable. And there's two ways that we can have a negative delta G. The first way is if the delta H is a large enough negative, then even if this is a positive value, once you have a large enough negative, you could have the final delta G still be negative. So what does it mean if something's large enough negative? It means if the change in energy is negative, it means it's exothermic. So in an equation where you have an exothermic reaction, but even if entropy is decreasing, and this is a positive value, it's still going to be thermodynamically favorable because it's enthalpy driven. Now the second way that you can get a negative delta G is by having your delta S be a large positive. Now what does it mean if something has a large positive here? That means even if your delta G is an endothermic and positive, you can subtract a large enough value so that delta G still remains negative. So entropy, if it's positive, what that means is it's entropy driven, and we have entropy increasing. So if you want delta G to be negative, you know that delta G is G final minus G initial. So this means that G initial needs to be higher or greater than G final. So Gibbs free energy is basically the amount of energy that you have to do work, but it's also a measure of how much that reaction wants to occur. So if we have something with a high amount of Gibbs free energy, then we know that it wants to go through a reaction. It wants to change. It's unstable and it wants to change. That's why when you have a high initial, you can get a delta G that's negative. And another question that I always get is are there deltas? Why isn't it just G equals H minus TS? So the reason we have deltas is just a practical reason. In a reaction, you actually cannot just measure the enthalpy of the reaction at a constant state. The way it's measured is actually the final minus initial. So you can use a bomb kilometer, to measure the change in enthalpy. So that's why you need the delta here. So you also need the delta in Gibbs free energy because you can't measure the constant Gibbs free energy. You can only practically measure the change.